She's going to speak about Luvian exceptional points in quantum thermal machines. Yeah, please go ahead.
Thank you. So good evening, everyone. First of all, I would like to thank the organizers for this very nice workshop with plenty of topics dealing with non-Hermitian physics. I'm learning lots of things, so thank you very much. So I will take this opportunity today to present you a recent work that I did with my PhD student Shishir Kandelval, who is in the audience, and Nicolas Brunner, a colleague in Geneva, which is about Luvian exceptional points, so in quantum thermal machines. So okay, it's not my habit to put a picture, no, because we are on Zoom. I thought maybe you know my face. My talk will be about thermal machines and Luvian exceptional points. So let me introduce to you these two aspects. So first here, so here just also I put a picture from Shishir and from Nicolas Brunner, who are my colleagues so in Geneva. To introduce the first aspect of our work, quantum thermal machines, let me try to motivate them. So quantum thermal machines are in general constituted of a working fluid, which has some quantum properties, and this working fluid is coupled to environments. And you can assume that these environments are biased either in temperature or in voltage, so that in fact your working fluid is brought out of equilibrium. And here, because I consider thermal machines, I will typically think about temperature biased environments. And in a thermal machine, what you want to do is to exploit your resources. So here's the environments to generate an output, and as output, so you can create work or cool an object or make a diode, control currents, tasks like this. And so if your working fluid is quantum, you can try to exploit several quantum properties, namely the spectrum, so the quantized spectrum, many body effect, quantum currents and entanglement. You can also engineer environments and the couplings, and for instance, to reach the dark states that the speaker before mentioned. And so there are plenty of works in that direction. And here I just put some examples of experiments or proposals. I must say it's really a non-exhaustive list, because that's really a field which is in full expansion for decades. So there are many works, but that's on the top left, that's an experiment where they did a heat engine using a single level quantum dot. So that's really exploiting like the quantized spectrum of the quantum dot. With some colleagues in Dublin with Haack, who was talking yesterday, we also proposed like a system with mobility age to enhance the functioning of heat engines. You can also consider, this on the bottom left, that's an exception in this slide, because in fact that's a classical engine, but working at the nanoscale. So just to say that the limit sometimes between classical and quantum is subtle, and we can still learn from these small classical engines when we are looking at what happens in the quantum regime. In the quantum regime, you can exploit like quantum currents and entanglement. So this on the top right, that's an example of an Aharonov-Bohm ring. Maybe that's something people know if you're coming from mesoscopic physics and quantum transport. And you can also try to exploit the information you gain when you measure a system. So that's on the bottom right. And also with respect to the information you have about the systems, there are like a bunch of works trying to see whether a Maxwell daemon can help you increasing the efficiency of your engine. So these are like just examples of questions that you can ask with quantum thermal machines and why they are interested. Now, so that's a family of thermal machines, you see, where the output is classical, no, because you want to produce work or to cool an object or to control the heat current. But in fact, there is another class of family, and I mention this because in fact in Geneva we have been working a lot on this system, which are like just out of equilibrium quantum system as before, but the output is not a classical task, is a quantum task or a quantum resource, namely quantum correlations in the form of entanglement. And so there the idea is really to use dissipative coupling to biased environment to generate your quantum correlations. So also it was like maybe a decade or a bit more ago, rather counterintuitive ideas that just from dissipation that you do not control, you can create quantum correlations. Now it's well accepted, but then still to demonstrate it's a challenge, no? So we call this entanglement engine because from out of equilibrium environments, which are our resources, we generate entanglements. So in this talk, I will first explain you a bit more in details these entanglement engines, because in fact, that's the basic model on which I will focus for the rest of the talk. And then I will go to the dynamics of this system. And for the dynamics, so I will look at an evolution equation that gives me the dynamics for the reduced density operator of the system and show you that there are Luvian exceptional points. And then in the last part, I will discuss the signatures of these Luvian exceptional points. So let me start with the presentation of the model. If you have questions, you can ask me. So this setup, okay, let me say it like this, that for this entanglement engine, you can, or for these quantum thermal machines, you can always try to first work out what happens if you consider a minimal model. So this is what we did with my colleagues in Geneva a few years ago. And the minimal model is, for instance, consists, for instance, of two qubits. So the qubits are two-level systems, which are interacting with a coupling strength G, and the interaction Hamiltonian is here. It's just a flip-flop interaction Hamiltonian. So it's very simple. And then there is coupling to the two environments. And here we considered the two qubits to be energy degenerate. That's why I have a single energy E characterizing the qubits Hamiltonian. So here I won't enter into too many details, but just to give you some properties of this system, one can first note that this system, the Hamiltonians describing the system are all time independent, the interaction Hamiltonian, the system Hamiltonian, and in fact, the couplings Hamiltonian to the environment too. And such that from a thermodynamics point of view, there is no work involved, there is no time dependence, and there will be only heat. So in that sense, there is no control. That's to be contrasted with, for instance, engineered quantum bars or engineered couplings, where you can control the couplings such that you can achieve an entangled state. But here there is only dissipation. And this is why also these machines are called, sometimes known as autonomous quantum thermal machines, because once you fix the Hamiltonians, you let the machine runs and you don't touch it anymore, and you can either wait for the steady state or just look at the transient dynamics. So why are these machines interesting? It's because, in fact, if you have two environments at the same temperature, so you do not bias them with a temperature gradient, you can show that the ground state and the state of your system will be a product state. And this is when you assume a certain regime of validity, a certain regime for the parameters of your system, which is a weak coupling to the environment and a weak coupling between the two qubits. And I will come back later to these points in a more precise way. So what is interesting is that you really need a heat current from hot to cold to sustain entanglement between the two qubits in the steady state. If you do not have this heat current, so if you do not use your resource, you do not have entanglement, and this motivates also the name entanglement engine. So just to show you one of the results, for instance, to characterize entanglement, there are different measures. And for instance, in this previous work, so we look at the concurrence. You do not need to know exactly the definition of concurrence. You just need to know that the concurrence, so is a measure. It takes the value 0 for 2 qubits in a ground state, and it takes the value 1 for maximally entangled qubits, so qubits in a Bell state. And what I just want to highlight, so this is the concurrence on the y-axis as a function of the hot temperature. Look please at the blue curve where we have fixed the cold temperature to be 0. And here you see that as soon as there is a gradient, a temperature gradient, then the concurrence becomes non-zero. And this is in the steady state, these curves. So we showed that. And then with Shishir, so last year, we pushed a bit more, so the understanding of the functioning of these machines. And we could show that there is, in fact, an exact relation between a transport observable, so the heat current, and the presence of entanglement. And sorry, we did that. Yeah, please, let me just finish this slide and I answer your question. So we did that for different interaction strengths between the two qubits. So it's not specific to a weak coupling assumptions. But here, what I would like you to see in those plots, on top, it's the heat current. On the bottom, it's the negativity, which is just another measure for entanglement. It also takes the value 0 for qubits in a product state. And what I want you to show is that as soon as the heat current was above a critical value, which is this dashed line, the horizontal dashed line. So for instance, if you look at the blue curve, then in fact, the negativity departs from 0. And so we could show the existence of a critical heat current for operating this engine. So these are like few results we got in the steady state regime to characterize the functioning of these machines. Yes, I'm happy to hear your question.
Yeah, so you said that in order to have entanglement in the steady state, you need some temperature gradient. So the two temperatures need to be different.
Yes.
So in the plot with the concurrence, I mean, I was expecting that in the yellow curve should be 0 before. I mean, the value of the cold bath is 0, 2. So I was expecting the other to be 0 before 0, 2 and then to jump somehow.
No, of course. So in fact, that's why I did not mention the yellow curve, sorry, because in fact, it's too much into details. But to give you a brief response is that the concurrence is a highly nonlinear value on the temperature of the bath, such that this is why you do not have like a departure exactly at 0.2. And moreover, is that these curves were obtained by optimizing over all parameters of the system. And so in fact, the part which is horizontal at 0, it does not exist because in fact, there were no concurrence, so we should not have plotted a heat current. Well, there is just no validity of our numerics in the region where it's 0. But I can come back to that later, maybe in a private. But it's just because it's not a one-to-one. When it's different from 0, then it starts. When the cold temperature is 0, then it's obvious. But when it's non-zero, it's not exactly at 0.2 that it starts. But if I would, okay, maybe more, sorry, now I'm thinking a more straightforward argument is that that's the plot for the concurrence. But if I would plot the heat current, then, okay, for the heat current, I will get a finite value as soon as TH is above 0.2. But that's not the case for concurrence. And okay, it's also because concurrence, you see, it characterizes entanglement, and entanglement, you need a minimal amount. well, you need some criteria on the off-diagonal terms of your density matrix, and this criteria is not fulfilled below this threshold.
So just a quick query. So you're still in the weak coupling limit, right?
Yes.
Because if you make the coupling strong, you always have those off-diagonal elements to be non-zero, right? In the density matrix.
So there will be non-zero, but there is not necessarily entanglement. And in fact, this is what we showed with Shishir in this work.
Okay.
Federico, I realized I was maybe, in fact, not so clear, but the answer is related, in fact, to what we did with Shishir last year, and I can rediscuss with you later. I'm sorry.
Okay, thanks.
Okay, so this is for the motivation for the entanglement engines, and it's not just a theoretical model, but there are like some proposals either with superconducting qubits or double quantum dots or with ND centers. And if experimentalists are interested to talk in more details, I'm always open to discussions. So now let me go to the dynamics of these systems. So here I will refer also to what was said in the previous talk, because it will be similar in the spirit that because we will be using a Lindblad master equation. So for the system, I have this Hamiltonian, which is the qubits, the Hamiltonian of the two qubits with energy degenerate spectrum with epsilon and the interaction term, which is the same as I showed you before. And if you only consider this as a closed quantum system, you will have a unitary evolution given by the von Neumann commutator. So the von Neumann equation, with the commutator. If you include the environment, then you assume some system bus interaction. And if you assume a weak system bus coupling and the Born-Markov assumptions, then in fact you will capture your dissipation with super operators, which are defined as follows. So this is the expression which I showed, and if your coupling between the two qubits G is smaller or of the order of the gammas, which are the coupling to the bus, then the operators that enters your dissipators are these local jump operators, sigma plus, sigma minus, which are just the raising and lowering operators for each qubit. So I assume people are a bit familiar with this, and such that at the end you can write your evolution equation for the reduced system made of the two qubits in a Lindblad form, which so accounts for the free evolution, so some unitary dynamics, and the effect of the environments. So we take into account the quantum jumps. So now, how do we go to non-Hermitian physics and to Luvian exceptional points? In fact, so here I just rewrote the Lindblad master equation. And this Lindblad master equation, you can write it formally as just a Lindblad super operator acting onto your reduced density operator. And this super operator L for the Lindbladian is non-Hermitian because of dissipation. Okay. So the general solution of such an equation, just a differential equation, so the solution is very simple, but the problem is that, of course, this L is a super operator and rho are matrices, no? So, and in general, L will not be necessarily diagonalizable, such that in general, this is not an easy equation to solve. But if your Luvian is diagonalizable, so with eigenvalues, which I call lambda I here, then you can write this Lindbladian as the diagonal form, its diagonal form and transformation matrices. And the solution then simply reads as follows, where you have that the solution at time t is just your transformation matrix S, and then you exponentiate your diagonal matrix. Because it's diagonal, it's very easy. So you just have all eigenvalues, and you have so the inverse transform matrix and your initial state. So if the Luvian is diagonalizable, it's very easy. So what I would like to emphasize here is that the spectrum of the Luvian sets the exact dynamics of the reduced quantum system. If you know the spectrum, in fact, you know how your system evolves in time. So let us come back to my 2-qubit system. And let me discuss a bit the spectrum in this case. So with Chichi and Nicolas, so we computed the spectrum. And for some values of the parameters, which are realistic within like a set of the art experiments, we could, the spectrum looks like this. So here I show you the spectrum in the complex plane. So you have the real axis, which is the horizontal axis, as you can see, and the imaginary axis, which is the vertical axis. And these are the eigenvalues. For those who are a bit familiar with superoperators, you may understand the dimension of our Luvian, because our 2-qubit system is a 4x4. So the density matrix of the 2 qubits has dimension 4x4. And so the Luvian, which is a superoperator acting onto this density operator, if you write it as a matrix, it will have the dimension 16x16. And this is why we have 16 eigenvalues. What is important, and maybe in contrast to the previous talk, is that here I am in conditions such that I have a unique eigenvalue, which has a real part equal to 0, and this will define me my steady state. So these are few remarks on the spectrums that we can make. So we have negative eigenvalues, which ensure that your system evolves towards a steady state. There is a unique steady state. The eigenvalues, they come in complex pairs. And now we want to exploit a bit this spectrum, And so we could solve analytically the full spectrum, but now to go a bit further in the direction of exceptional points and Luvian exceptional points, we will just reduce the dimension of L, and this is valid without entering into too many details if you choose certain initial states, but it does not lead to a loss of generality of our results. So if once you have the spectrum, I told you that it sets the dynamics of your system, So if I show you again this equation, this you can rewrite it as follows, where it's just the sum of some coefficients that depends on the initial state. You have the exponential of your eigenvalues and the right eigenvectors of your Luvian. The first eigenvalue is a does give you the steady state. So this is what I call rho with the subscript SS for steady state. And then I have the remaining sum. And these right eigenvectors, they in fact correspond to decay modes, because they correspond to decay mode in the transient time before you reach the steady state. So when we reduce the dimension of the Luvian, in fact, we do consider initial states such that we are only dealing with the spectrum with red dots and our steady state. And so now what happens is that my sum only goes from 2 to 5, because the first eigenvalue is the steady state is 0, and I have 5 remaining eigenvalues. Okay. At what time did I start, Manas?
Yeah, I think Juzar, can you, Juzar is...
yeah,
Juzar,
sorry. Hey,
I think it was 15 or 20, no?
Yes,
or,
so you have about 15 minutes.
Yeah, okay, so it will be completely fine. Thank you. So, okay, now let me look at this reduced spectrum with you. So I have one eigenvalue which is 0, that's the steady state, and I have the remaining ones. And for clarity, I gave you the exact expressions of these eigenvalues in terms of the parameters of the system. So you see that they are quite simple, no? And they depend on the dissipation rates of the that characterize, so on the coupling rates that characterizes dissipation to the environment. So gamma is just the sum of gamma 1 plus gamma 2, and delta gamma is the difference, the average difference of these two rates. And maybe you have not seen, sorry, I forgot to put it again on this slide, but this big gamma 1, gamma 2, just for clarity, I define them. Okay, maybe I forgot to write it, but these are the sum of the incoming rates and outgoing rates. So it's gamma plus gamma minus for each bus. Okay, so these are technicalities, but I wrote them here. But it just to tell you that everything is properly defined. So we have these eigenvalues, and now we know that exceptional points, no, they correspond in general when you have a non-Hermitian matrix with eigenvalues at the coalescence of eigenvalues and the corresponding eigenvectors. Otherwise, you would have only what is called diabolic points if the eigenvectors do not coalesce. And so here we could show that we have a Luvian exceptional point. It's just a single one, sorry, it's a third order one because we have the coalescence of 3 eigenvalues, namely lambda 4, lambda 5, and lambda 6. And this happens when you see what is under the square root is equal to 0, because then you have 5 and 6, lambda 5 and 6, which is equal to lambda 3 and 4. But it's only a third order exceptional point and not a fourth order, because we do not have the coalescence of the eigenvectors for corresponding to the third eigenvalue. So just to highlight that you have to be very careful, no? When you look for exceptional points, you must satisfy the coalescence of eigenvectors. And so the condition for which this exceptional point is the following one, that again, as expected, depends on the parameters of the system. And what is nice is that you see, again, if you fix the coupling to the bus, you only have to change the coupling between the qubits to achieve this to reach this exceptional point. So I motivated at the beginning this because I told you I wanted to look at the dynamics of my 2 qubits if I put myself again in the context of a quantum Sommel machine. And so now it was a bit technical. No, I have to look at the Luvian, but what's the consequences of what I told you on the dynamics? So to know that, I have to write again the solution for the new Luvian, which has these 3 exceptional points. But as I told you, the eigenvectors, they coalesce. And so for people who are familiar with the field, so it means that you do not have anymore a complete basis at exceptional point. And so you must construct this, what is called this generalized eigenvectors. And with that, you can write the Jordan form of your Luvian and again get the solution of your differential equation for the density operator. So this is what I will briefly sketch to you now. So this is like my Luvian with the 3 exceptional points. And now to be able to work in a complete basis, I have to look at I have to construct the Jordan form. So the Jordan form is typically it's with the eigenvalues on the diagonal, and you have this 1 in the upper part of your matrix. And now you may wonder why I put some finite coefficient alpha and beta, but in fact, it's motivated for physical reasons, because here it's not only math, it's about physics. And the object I'm dealing with are density matrices. Okay, at the end, I want to have a valid solution for density matrices. So I have to give some freedom in my Jordan form, which is like with these coefficients alpha and beta, to be able to normalize my right eigenvectors to get valid density matrices for my solution. Okay, so this is just a freedom we need to satisfy the properties of density matrices. So this is for the Luvian. And now for the solution, I can exponentiate the Jordan form of my Luvian. And here it gives so this typical structure where you have the exponential of the eigenvalues, E lambda t, the different ones. But then because of the Jordan form, you have this typical factor t here and t squared that appears in front of some off-diagonal terms. So I told you, before that the dynamics is set by the Luvian. So if I modify the spectrum and this matrix, dynamics is expected to be modified. But the question is how and whether there are some specific signatures. So this brings me to the last part of my talk.
Géraldine, I have one
Yes.
question. So I'm still restricted to a subset of initial conditions, right?
Okay, yeah, it's not a subset of initial condition, it's a subset of initial states, well, yeah, okay, of initial conditions. But in fact, the only thing that we demand, well, it's for, we have the general solution, but the only thing we demand for simplicity is that we deal with initial states which have non-zero elements at the same place as the one which will remain in the steady state. And if you remember so I told you that with these engines, I have entangled steady state. And so what I will get at the end are just finite value in my density operators on the diagonal and just two non-zero elements on the off-diagonal terms. And so I restrict initial state to this class of to be states with non-zero elements only at those positions.
Right, right. If you go to the previous slides where you had this eigenvalues on the real axis, negative real axis.
Ah, yes.
Right. So here, I thought you were restricting. Okay, so I got confused about the initial states. Is there any restriction on the initial conditions?
No, well, initial state, I will restrict the class of initial states, but it's not, as I will see, I can consider a ground, the qubits to be in a ground state, in a mixed state, in a thermal state, in a singlet state. So it does not restrict the properties of my initial state. I just restrict the number of non-zero elements initially.
Okay, okay.
That's why with that, I do not lose in generality.
Right, right. So your
maybe,
Luvian, right.
Yes?
So your Luvian is now a smaller dimensional matrix.
Exactly.
So you ignore all the eigenvalues in the
Yes.
imaginary this thing.
Well, exactly. I ignore all these imaginary eigenvalues, which will give some oscillatory behavior.
Right.
But with Shishir, we derive the full solution. So in our work, we have their expressions, and we could show that we have second order and fourth order exceptional points and simultaneous exceptional points. So all these points, specific points, are expected to affect the dynamics. But in fact, to get a clear signature on how it affects, this happens more on the real axis, and this is why we focused to this reduced Luvian.
Okay, okay. I see. Okay. So even the other eigenvalues can come and collide, right? They can also come.
Yeah. So there are plenty of exceptional points in this.
Okay. Okay, okay. Thanks.
So this coherence is what you're retaining is between the single excitation sectors, is it?
Yeah, exactly. These are the terms exactly corresponding to my flip-flop interaction Hamiltonian, so the 0, 1 and 1, 0 term.
So it looks like your Levelian has the weak symmetry in the sense Jujar has introduced. So you are essentially working in the subspace corresponding to some sector of that weak symmetry. It seems like weak symmetry.
Yeah, it could be.
Yes.
Yeah, we never thought about this in those terms, but it could be, and that's indeed an interesting aspect to see how it is related to the previous talk.
Yeah, it looks like it's a adjoint of sigma z plus z1 plus sigma z2. The commutator looks like the weak symmetry here, and you are working in the sector which corresponds to the eigenvalue of that weak symmetry in the Levelian space with 0. Because all the populations and the coherences, the difference in the excitations looks 0. So it looks like you're working in the subspace of the weak symmetry.
Yeah, good remark. Thank you. Okay, so now let me come to maybe the last and maybe most important part. So the signatures. So there is one obvious signatures you can look for, and it comes from the math. No, it's a signature where you would like to investigate this polynomial in time dependence of your solution. And this will happen at intermediate times when you're able to probe the decay modes associated with these subspaces. So I will come to that a bit later. I would like first to make some general comments. No, there was this. So, okay, Levelian exceptional points have to be distinguished from non-Hermitian non-Hermitian exceptional points. And yesterday and in the previous days, there were several talks looking at non-Hermitian Hamiltonian exceptional points, where people, they look at open quantum systems, but then they neglect quantum jumps. And in fact, for those systems, when you neglect quantum jumps, so you follow a semi-classical approach, it has been shown that there is an enhanced sensitivity at the vicinity of exceptional points, and this is quite now well known and investigated in several systems. But when you deal with Levelian exceptional points, in fact, they are much, well, at least to the best of my knowledge, there are fewer works, and signatures are more subtle or harder to determine. There is one group which has contributed a lot. That's the group and people around Frank Honori. And here are two papers where, in fact, there is claim signatures in time order correlation functions. I put the reference for more details. And also they try to see what's the relation between non-Hermitian Hamiltonian exceptional points and non-Hermitian Levelian exceptional points. And this topic is I think a current research interest, and Haack briefly also mentioned these questions of quantum jumps yesterday. And so here it's clear that we take the quantum jumps into account, but then it makes the characterization of exceptional points much more complex. But why were we motivated to do so, and why did we have a hope that it will work? It's because you all know an exceptional point, a Levelian exceptional point that has a very clear signature. And this is the case when you look at the damped harmonic oscillator. You all know this system, and you all know that when the damping coefficient is equal to the eigenfrequency, so when the damping coefficient squared is equal to the eigenfrequency squared, then you reach this so-called critical regime, and that's the regime where you reach the steady state in the fastest way. And so, in fact, if you write the corresponding Levelian for the damped harmonic oscillator, this critical regime exactly happens at the exceptional points of the Levelian. And so we were wondering whether there would be a similar behavior in the entanglement engine. So to look at this, you have to define a measure, something to be able to characterize this decay to the steady state. For this, I just define it for completeness, but we looked at the trace distance, and the trace distance between a state rho and, for instance, the steady state is defined with the norm 1, and here is just the mathematical definition. And so this trace distance, it reaches the value 0 when your system has reached its steady state. So now let me show you our results. So that's the trace distance as a function of time. And I show you the curves for different initial states. So a singlet, so they are quantum currencies, a ground state, and the 2 qubits in a thermal state, which are defined with respect to the temperatures of the 2 baths. So these are my this is my time evolution. And of course, what you can see is that it's exponential as you expect. It decays exponentially towards a steady state. Now, when I turn the parameters of my regime such that I reach the exceptional point, then I get these dashed lines. And you see that if I zoom at large time, please look at all dashed line compared to the solid lines. And you will see that all dashed lines at long times, they are below the solid lines. So why is this remarkable? In fact, it's remarkable because EP are expected to affect the dynamics, but not necessarily to correspond to a critical damping. And so this will have applications for different steady state engines where you want to reach the steady state in the fastest way, in the fastest possible way. So in the work, in fact, we did a more quantitative analysis. And for this, we looked at the ratio of the trace distances at EP and at non-EP. And what you can see is that at long times, it's clearly below 1 and it reaches 0. And so this means that at EP, you always go faster to the steady state than at non-EP. In the intermediate region, which is blurred here in gray, you cannot say something because it depends too much on the initial state. So here I show you the plot, but because I think it will be soon, my time will be soon over. Here it's just a sketch of the proof where we could write the exact solution of our density operator at time t as a function of the parameters of the system. And then by plugging in the exact form of the eigenvalues, we could insert it in the ratio of the trace distances that I defined you before. And when you took the limit, because you have some exponential components in the denominator, which are, you see, increasing with time, you can show that at long times, this ratio will, the limit of this ratio will go to 0. Okay, so then the more, yes?
Sorry, 2 minutes more.
Yeah,
at the most.
okay.
No, thank you.
Okay, perfect. So, okay, it's perfect. I will be done. So now for the short time dynamics, which are like the most obvious signatures that you will look for because of this off-diagonal terms in the exponential of the Jordan form. We also looked at them. And here, in fact, to see these signatures at intermediate times, you need to probe exactly the decay modes. So you need to probe the subspaces in which this will happen. And to this end, you have to engineer specific initial states. So this is like a less general feature, a less general signatures, okay? You have to engineer the initial state. Whereas for the critical dampings that I showed you before, you can do that for almost all initial states. So with specific initial state, here I showed you this plot, I think, which is quite intuitive. What I showed you, so sorry, I forgot, on the x-axis, that's time. And the black dashed line is an exponential decay that you would expect if you will not have some exceptional point. But then on the y-axis, you see I plot the logarithm of the trace distance, of a normalized trace distance, and I plot the logarithm to really see the deviation with respect to the exponential. And so you clearly see that the different colored curves, which corresponds to engineered initial states, they clearly deviate from a linear decay that corresponds to the exponential decay. So that's the clear signature of this polynomial in time dependence. Okay, so with that, I come to my conclusion and with some perspectives. So with this simple system, we could solve analytically the full dynamics and show the existence of different orders of Luvian EP, importantly for state-of-the-art parameters. We could so connect a bit the field of open quantum systems and so quantum summable machines with the field of non-Hermitian physics. And I think what is quite remarkable is that we could show that there is critical damping at exceptional points in an open quantum system. And that's a clear signature of a Luvian exceptional point, which is much less obvious than signatures of a non-Hermitian Hamiltonian exceptional points. So here is a reference, and as for the perspective, so we are interested in understanding a bit more in detail, so the difference between non-Hermitian Hamiltonian and non-Hermitian Luvian, what it will give in the context of quantum summable machines, and really now exploit this physics for optimizing summable machines in time or for optimizing thermodynamic cycles. And then in my slides, you will find also a bunch of additional references. So with that, I thank you for your attention.
Thank you so much, Géraldine, for this very nice talk. If there is a question from the audience, just one quick question. We have had quite a few already. So
I have a question.
Go ahead, Takis, please.
Yeah, hi. Thanks for a lot for your talk. So actually, a question comes to my mind is like you showed that this is a resource for many things, this exceptional point. And I was wondering whether it could also be maybe a resource for amplification, like for a different kind of machine where which we're talking about. So what is
yeah. So thanks, Takis, for your question. So in fact, that's something we are looking at with Shishir. But as I said, finding application for this Luvian EP, it's much less obvious than finding applications for non-Hermitian Hamiltonians. Because for non-Hermitian Hamiltonians, and in many papers, you will see these typical density plots where they show that something happens in the vicinity of the EP at the eigenvalue. And then many papers, they claim there is an enhanced sensitivity, and probably you can use that also for amplification, as you said. But in fact, for this Luvian EP, you cannot at least find something so obvious. We looked at several quantities, transport observables, I did the density plot and so on, and it's not so obvious. So the critical damping is something we got, and we were already quite happy with that. But it's really an open question, and I'm happy to get some insights if you have some ideas and to further discuss, because that's definitely something we want to look at.
Okay, thanks a lot.
Yeah.
Okay, great. Let's then thank our speaker, Géraldine, once again, and go on to our next talk. Thank you, Géraldine.